All right. So today we're going to talk about 3.1, defining the derivative. Okay. If anyone has taken calculus before, or maybe talked with friends about calculus, or read a little bit about calculus in advance, this word derivative is going to be one that we become really familiar with. Okay. But as we sort of begin our journey into this next chapter, we want to think about what we know, right? And so one of the things that would be really important from the last 2 weeks is what is a limit and how do we find limits? Okay, so we've talked about a lot of different ways to find limits. I've intentionally left them out here because I want us to think as we're studying, oh, what are those different ways? How do I know when I'm being asked to do that particular method? Okay. All right. The second thing, what is continuity and how do we determine continuity versus discontinuity? And the last thing that we're going to talk about here is slope. And this we haven't seen in our class yet together, but it's something that I want us to do just a little bit of a Monday morning brain dump on slope. Okay. And so, what do we know about slope? Tell me things that pop into your brain when you think about slope. All right, see a couple things in the chat here. All right, so great. All right, so we've got m equals rise over run. That's maybe a throwback to like our middle school days where we were, or early high school days where we were just plotting points and trying to figure out how that makes a line, right? We definitely talked about the y equals mx plus b. That is such a classic equation that we use. What's the m stand for here and what's the b stand for? Right, m is the slope, exactly. Great, and b over here is our y-intercept, okay? What's another way that I could write rise over run? Anybody remember like a different equation that we could do? Y over x. Okay, that's pretty close to what I was thinking. Yeah. Right, we were thinking more like y2 minus y1 over x2 minus x1. Right, exactly. Change in the rise over change in the run. Perfect. Okay. Now, one of the things that I do want to sort of jot down for us to start to think about is this y equals mx plus b is an equation that we all know, that we use pretty frequently. But one of the things that we're going to do, particularly in the next chapter, we're actually going to be looking at a different version of this equation, okay? And in fact, it comes from this. M equals y2 minus y1 over x2 minus x1. And so if I write this m again down here, can someone tell me how would I get the numerator all by itself? Like how would I get y2 minus y1 all by itself?
By multiplying the x2 minus x1 both sides, right?
Exactly. We take the denominator, we multiply it to the other side, right? And so it turns out that we get this other equation that looks like this. Y2 minus y1 equals m times x2 minus x1. This is going to become a way more valuable equation for us to think about when someone says, write the slope of a line or write the equation of a line, we're actually not going to use this one. We're going to use the one that we have written here in the pink. Okay. Now that's sort of something to think about for the next chapter. So I don't want to spend too much time on it, but I just want to put it out there that there is going to be a different version of y equals mx plus b that we're going to find more useful. Okay. So what do we know? We know limits, we know continuity, we know a little bit about slope. And what's new? So we have two main questions for 3.1. Okay. In particular, we're going to be looking at something called an average rate of change. And we're going to be looking at something else called an instantaneous rate of change. Now, these phrases come up so often that I tend to abbreviate them. So A, R, O, C. You'll often see me write a rock, right? I don't think you'll find it in a textbook, but it's just my way of abbreviating average rate of change. And similarly, instead of writing instantaneous rate of change, I will write IROC, okay? And so one of the things I really want us to walk away from 3.1 with is how are these similar and how are they different? Okay, so kind of keep that in mind as we're going through things. How are these similar and how are they different, right? So with that, let's get started with a little warm-up question, all right? So we've got a graph, right? And we're gonna take a look at this graph and we're gonna answer some questions about it. All right, so the graph below shows the positions of two runners, runner A and runner B. They run a 100-meter race and they finish in a tie, okay? So take a look at this graph. And the first question here is compare how the runners run the race, right? So we've got runner A over here. And then separately, we have runner B. Okay. So take a moment, think about how these two runners are approaching the race. Are they approaching it in the same way? Are they approaching it in a different way? What would it look like if they were running and you were watching this race? And when you have some ideas, you can either unmute if you find it more useful or more efficient to share your thoughts, or you can go ahead and type into the chat.
Well, runner B starts off, yeah, like running like less meters per second, basically.
Mm-hmm.
So as more time passes, they like start to accelerate. And so they start to cover more meters and then they reach the finish line at the same time.
Yeah.
So they're basically like conserving their energy.
Okay, I like it. I like it. So they're sort of off to a slower start and then they start to pick it up. And by the end, they're actually running faster than runner A, but they had to run faster to catch up, right? And so I see a lot of the same thoughts in the chat. A is a constant speed and B is changing their speed. Runner A has a consistent speed. Great. So let's write down some of these thoughts. All right. So runner A is constant speed, right? Or constant rate. And runner B starts slow and gets faster. All right. I think that's a pretty great start. I do want to say, though, one thing that this picture does not show us is the path that they take. Okay, so meaning it isn't that like runner A goes in one direction and then runner B goes in a different way and they get to the same point, okay? But rather this is telling us like the speed that they run to get to that place, all right? So runner A is running very constantly, same meters per second the whole time. And then you have runner B who's like, maybe they didn't hear the gun go off at the start of the race. And then they're like, oh, shoot, I got to catch up. And so they sort of sprint really fast to get to that finish line at the end and manage to catch up to A and happen to tie the race. Okay. All right. So let's start to put in some of these terms that we talked about. In particular, what is the average velocity of runner A? Okay. How would I think about velocity as someone had said, like change in y over change in x? How does that apply when we want to find the average velocity of runner A?
I mean, can't we just take like, I mean, just they were running in the beginning of the race, like, and then compare that to the end. So like 0, 0 and 0 for the white one, and then I think 100 to 14 for Y2s and X2.
Great, great. So your response and Jordan's response, I think, really give us the full picture of what we're looking for here. All right. So average velocity is indeed what Jordan typed into the chat, which we can write as the change in distance over the change in time. All right. Now that corresponds to, on our graph, we have distance on the y-axis and time on the x-axis. So that's the same as saying change in y over change in x. And we can do exactly what Utku said, which is find this point. All right, and we got 0, 0 here, and we've got 14,100 over here, all right? And if we put those into our x2 minus x1 on the bottom and y2 minus y1 on the top, we're going to get 100 minus 0 over 14 minus 0. I think we can reduce that to give us 50 over 7. And the units here would be meters per second. Okay. This gives us the slope of that line. I think we sort of answered this already, but take a look at question C here. When is the velocity of runner A the slowest, and when is it the fastest?
Isn't it constant, so it never changes? So it's always the same.
It is, yeah, it's kind of a trick question here. Earlier, folks, I think we pretty much agreed that this is the constant speed or constant rate the whole time. And so if someone is saying, what is the velocity? When is it the slowest? When is it the fastest? We can simply say that A has a constant velocity, right? A has a constant velocity and is always running 50, let me write that better, 50 over 7 meters per second. Okay, so the rate at which runner A runs doesn't change, right? That's the same thing as saying the average velocity is constant the whole time, right? But let's try and answer this same question for runner B, okay? So maybe we pick a different color and see what's happening with runner B, which is more like this bottom curvy part here, okay? And so how would we find the average velocity of runner B?
I just thought about, wouldn't it be the same since they came up, since they ended up at the same time? I don't know. I just thought about it. Probably not.
Yeah, okay. Well, I think question B and question D look pretty similar, right? They both say, what is the average velocity of the runner? And so the average velocity is always from when we start all the way to when we stop. If we find the y2 minus y1 over x2 minus x1, that's going to give us the average velocity, okay? So what do we think, folks? Can we, like Utku said, can we use the same 2 points to find our average velocity for runner B? What do we think? Yes, no? I heard a yes. What do other people think? Yeah, it turns out we can, okay? So we are going to do a little bit of this copy paste situation because I'm on a technology and I can, right? But the reason we can do that is because they both start and nobody's running, right? At the first, at the 0 second, the time we started the clock, they're both on the start line. And at the time we stop counting, they've both traveled 100 meters in 14 seconds. But sometimes it's not just like where you start and where you stop, right? But rather what happens in between. And so question E, when is the velocity of runner B the slowest and when is it the fastest? Let's see if I can get that all on one screen. What do we think? When is the velocity of runner B the slowest and when is it the fastest?
I think in the beginning it's the slowest and at the end it's the fastest.
Yeah, looks like Dallas agrees with you there. And I would agree, like this, kind of got off to a slow start, but then had to sprint real fast to catch up. All right. Now, how could you describe that in terms of the slope? Like, how does this slope compare to this slope?
Not sure.
Okay. This is an open question. What does everyone else think? The two slopes of those red little segments that I just highlighted here. Less versus more. Okay, that's pretty short and to the point. Slope is less steep at the start and then it increases later. Yeah, this slope is pretty flat. And then this sort of gets steeper and steeper and steeper. So at the end, the slope is the most steep, right? And so that gives us a little bit of language to answer this question here. When is the velocity of runner B the slowest? We can say B has the slowest velocity at the start. We can say least steep slope, right? And has the fastest velocity at the end, because we have the most steep slope. So let's kind of get this all on one page here. So again, we just have these two runners. They're running sort of the same distance, but they run it differently. They approach the race differently, right? And so some of you in that partner interview I asked you to do like the very first day, some of us sort of described what we hope our trajectory in the class is, right? We hope that that experience is sort of steadily upwards. And some of us were like, oh, sometimes the beginning of the semester is like hard for me to motivate. But then at the end, I sort of like really, you know, focus in on what I need to do, and I still walk away with the grade that I want. So you could also imagine this as like that kind of visual, okay? All right, any questions on this graph before we move on to our rates of change? All right, so let's take a look at more pictures, right? So we've got example 1 right here, and it says, draw a dot on the graph where x equals 20. What is the y value of that point? All right. And so let's take a moment, and whatever you think that y value is, go ahead and type that into the chat. So what is the y value when x equals 20? Yeah, I would say it's about 300, right? So y equals 20 is about here, and that y value is about 300. That's a great estimate. Okay, let's draw a dot on the graph where x equals 60. What is the y value there? Looks like Stefan has posed 700 as a value. Looks like a bunch of folks agree. I think that's a pretty good estimate. Great. Okay, now part C, find the slope of the line that connects the 2 points you drew in A and B. So we would want to find the slope of the line that connects the orange dot to the pink dot, right? What formula should we use to find that slope? The slope one, okay. In particular, we could use, y2 minus y1 over x2 minus x1. Great, thank you, Norm. And we can go ahead and plug in our values. What values should we have on the top? Great, I agree, 700 minus 300. And the numbers we have on the bottom? Great, 60 minus 20, that gives us 40. All right, and so if we reduce here, we end up with a slope of 10. All right, not too bad, right? Okay. Any questions on example 1? Marking some points, finding some slopes. All right, let's take a look at example 2. All right, so I'm going to give you a couple minutes to work through this in the privacy of your own learning environment. And then we'll sort of put some workup on the screen together and think about what that picture was going to look like. Okay, so take a moment, see if you can figure out part A, how do we compute that? And then part B, maybe the more important part actually, how do we draw that? All right. Anyone have any values that I can plug in here? What would I put instead of f of 40 minus f of 10? What two numbers could I put up there?
200 and 400.
Yeah, 200 minus 400, which we know will give us negative 200. Great. And then in the denominator, we already have the 40 minus 10. That could be 30. Yeah. And then if we simplify this, we'll get negative 20 over 3. Great. All right. So computing things, putting them into play, but how do we draw this answer on the graph?
Sorry, Professor, I got confused when I was doing this because f of 40, I thought that would be considered like y1, and then f of 10, I thought that was y2, and then you flip it.
Oh, well, so whatever order we have here, I know we're used to having like the bigger number in the front and the smaller number later, but it doesn't have to be that way.
Okay.
Okay. Yeah, that's
Thank you.
That's a good point. That's a good point. We should have clarified that, right? But if we were to draw a line connecting the points, right? This would be considered our point. That would be right about here. And then separately, we would have f of 10 and 10, and that would be over here, right? So the order in which we do it doesn't actually matter, like the order that we plug it into the equation, but when we connect them, I think it becomes a little bit more clear that we do indeed have a line with a negative slope. So it's okay that we get a negative answer out.
That makes a lot of sense. Thank you.
Okay, cool, great. All right, so this is the blue line and has negative slope. Okay. All right, so very classic feel to calculus here, where we know how to do things in a particular way, right? But then sometimes the way the question gets asked, it asks us to answer different parts of the question, right? So I didn't say like, draw this dot, draw that dot, then find the slope. I was like, let's make sure we know our function notation, that we can find points on a graph. And then this is a negative number, but that's good because when we look at the picture, it does indeed have a negative slope. Right. All right. Any questions on example 2? All right. Let's take a look at example 3 then. All right, so more pictures here. In fact, the same pictures, but just different questions about them. All right, so let's start with question A over here. Question A says, identify 2 points where the slope of the line connecting them is 0. So I'll give you folks a few moments, all right? And let's see if we can come up with 2 points that have the same, that when I connect them, I'm gonna get a slope of 0, right? First of all, what does a line with a slope of 0 look like? Okay. So in case we weren't sure, right? A horizontal line has a slope of 0. And maybe we'll put a little picture here just to remind ourselves that this is what a horizontal line looks like, right? I know we have so many different vocabulary terms, but we want to remember a horizontal line goes sort of side to side like this, okay? All right, I see some ideas in the chat. So Marilyn has put in f of 10 and f of 50. So 10 and 50. Yeah, if we connect those two, we're going to get a horizontal line, and that has a slope of 0. I love it. I love it. So great job, Marilyn. All right, let's see. Kelvin says 0 and 55. So at 0, we have this, and 55 is about here. Yeah, I would say if we connect these, we could definitely get a slope of 0. Great. And I think, Jordan, you're a little bit more accurate there, maybe the 0 and the 58, right? But I would say 55, 58. I'll take it either way. I know what we mean. All right. Let's get another pair of points that where I connect the line between them and I get a slope that is 0.
Maybe like 20 to 45.
All right, 20 to 45. Ooh.
Yeah, somewhere out there.
Yeah, I like that. I take that. That is definitely a slope of like 0. All right, 39 to 41. You're going to make me zoom in real close here and show you how bad the quality of the picture is, right? Maybe like 39 and 41, something like that. Yep, I like it. I like it. 60 and 80. Ooh, looking at a different part of the graph we haven't really looked at yet. So it looks like maybe 60 and 80. Ooh, give me a different number. Change the 60. Change the 60 a little bit, because I think you're on the right track. How could we change the 60 so that this becomes a horizontal line now? Like it's perfectly straight across. Yeah, maybe like 63 or something like that. Here to here, I would buy that those would give you, yeah, or 65, right? Perfect, perfect. But all of those would give you a slope of 0. Great. Okay. So a way to sort of summarize this is choose any 2 points that have the same y value. This guarantees that the line connecting them will have a slope of 0. Okay, so every single answer that we got here is great. So we had like maybe this was one, like Alex's suggestion of up here. This was also one. Someone had suggested this line, right? So all 3 of those pink lines are examples of 2 points where the slope of the line connecting them is 0. Okay. Great. Let's take a look at part B. Different question. Which is larger? The slope of the line connecting x equals 40 to 60, or the slope of the line connecting 40 to 70? All right, so I'll give you a moment to kind of think about that, but then we'll go ahead and maybe make that line in green, and used orange a lot today, but we go purple for the second line, okay? So what do we think? Which one is going to give us the larger slope? All right, we've got 1 vote for maybe they're the same. What do other people think? Okay. Let's see. We've got maybe 40 to 60, 40 to 60. All right. So let's go ahead and try and draw these in. Okay. So let me attempt to draw these. 40 to 60 is going to be here. How's the Monday morning drawing going to go? We're never quite sure. All right. So we've got that. As the green line, and then the purple line would be same starting point, but going to 70, which is here. Oh, that's a terrible line. Let's try that again. Oh, that's better. Okay. All right. Now that we've drawn them, what do we think? Which one has a greater or larger slope? Yeah, now that we've drawn them, we can see, right? This green one is a little bit steeper than the purple one. Just goes up a little bit faster, okay? All right, so if we go back in and we answer the question, we can say that the green line has a slightly steeper slope. Great. Let's take a look at the next question.
I have a question.
Absolutely. What's up?
So if we let's say you didn't graph it and you just gave us the question without the graph, then would we, and we had the points though, so we had the X and Y points, then would we just find the slope of them and compare?
Yes, exactly.
Great.
Wonderful. Oh, I love these questions, right? Because it also means that you've been learning how I like to think about things, right? Which is that graphs are all fine and good, but like, how do we answer them without a graph? You could just find this X, Y value, find this one, and I bet that would help you figure out that slope, okay? So great connection. All right, so let's take a look at these last 2 questions here. Is the slope at X equals 10 larger or smaller than the slope at X equals 30? Explain how you know. So let's think about that a little bit. Is the slope at X equals 10 larger or smaller than the slope at X equals 30? Okay, we've got larger, but in a negative way. Okay. How would I draw the slope at 10? Anybody have any ideas on that? Oh, yeah, right. That's sort of weird, right? Calvin, you posed the exact question I was hoping someone would ask. Don't you need 2 points to formulate the slope?
Yeah, I was thinking, like, since we didn't have a range, how are you going to be able to determine that?
Great. Well, I'll tell you, later on today, we're going to find out the answer to that. Okay. It turns out that we're going to be able to sort of like zoom in really, really close. All right. And you know how in this previous question, I drew a few sample lines, but one of them that I was sort of joking with Dallas, I was like, oh, he picked like 39 and 41. I was like, oh, you're going to make me like zoom in really close there and find those 2 points. But that did in fact give us a horizontal line. Okay, so let's kind of imagine then if in this picture, right, to find the slope at x equals 10, what if I picked like 9 and 11? So like 9 and 11. Now I kind of have 2 points and I can sort of draw a slope of a line that goes through both of those. Okay, that's going to be what we're really looking at in the second half of today's lecture. What could I choose if I wanted to estimate the slope at x equals 30, the red one? Like what might be some good x values to draw on here? Sure, why not? 29 and 31. So maybe like here, here. Okay. And if I connect those, I get something kind of like this. Okay. So now that we have maybe a more clear picture, let's look at this question again. Is the slope at x equals 10 larger or smaller than the slope at x equals 30? What do we think now that we can see this blue line and the red line? All right, so maybe.
Yeah, I want to say it's larger at 10 as well.
Ah, exactly. Okay, so let's write this out. The slope at x equals 10 is more negative than slope at x equals 30. Okay, be careful here. Which one has the bigger value? Like in other words, is negative 10 bigger or smaller than negative 5? Okay. So therefore, the slope at x equals 10 is smaller than the slope at x equals 30. Okay. So if we're thinking about positive and negative numbers in sort of the traditional sense, this slope is, that slope is a smaller number than this slope. Okay. All right, let's take a look at one more picture, and then we're going to go ahead and sort of summarize 3.1, okay? So question D, which is larger, the slope at x equals 60 or the slope of the line connecting x equals 40 to x equals 80? Now I think the green line, we can all sort of imagine how we might draw that, like 40 to 80, and we can connect that. That was terrible. Let's try that again. Okay, so we've got this green line here. What numbers might I try and draw two dots at to sort of get the idea of the slope at x equals 60? Yeah, maybe 55 and 63, maybe even like 59 and 61, right? Like the closer we can get to this 60, well, the closer we can get to 60, maybe the more accurate our diagram will be. All right, so which one do you think is larger, the slope of the yellow line or the slope of the green line? The yellow one, right? Yeah, so the slope of the yellow line is larger than the slope of the green line. Okay. All right, so thanks for playing along. I know I've asked you to look at a bunch of pictures and we're just sort of exploring this idea of slope, but I promise you that this has to deal with our entire next chapter. All right, so the entire next chapter, but also the very important bridge between chapter 2 and chapter 3. Okay. All right, so let's take a look at our summary, right? On the summary page, I want to talk about the average rate of change and the instantaneous rate of change, right? So those are two phrases that we said at the very beginning we were going to want to compare. We haven't really brought those terms up again as we looked at these pictures. So we've got our average rate of change and we've got our instantaneous rate of change, okay? But we've actually secretly been talking about these. So where are we secretly talking about them? It turns out that the average rate of change, okay, is when we have some sort of graph, right? So maybe our function looks like this, and let's call this f of x, right? And I'm going to pick 2 points on there. I don't know where they are, doesn't really matter. But let's say that we have, pick a different color. Let's say we have 1 point here. If I tell you the x value here is a, what would you tell me the y value is at that point?
B.
I don't know for sure, but I do know because my function is the f function, I could actually call this f of a. All right, so we're saying we have an x value of a, we plug that into the function, we get f of a. All right. let's choose a second point somewhere else along the road. And I call this x value b. What would you call the y value here?
B of A. I mean F of B, sorry.
You got it. I know what you were trying to say. F of b. Okay. All right. Now let's say we connect these 2 points. See what we're doing? We're connecting these 2 points with a line, just like we did in some of those previous questions. How, my friends, would you find the slope of the line?
By following the formula.
Okay, so we could say the slope is f of b minus f of a over b minus a, where this is the green point, this is the pink point, all right? There's one more vocabulary term that I want us to walk away with here, and that is when we draw a line that goes through 2 points like this, we usually call this the secant line, okay? So this is called the secant line, all right? This is also another way of saying find the average rate of change. So in all those pictures that we looked at before, and I would encourage you to go back to those pictures, maybe during the break or maybe later, every single time I was like, here are these 2 points. I want you to find the slope of the line between them. I was secretly saying, can you find that average rate of change? Or can you find the slope of the secant line? Okay, so secret ways of asking the same question. So average rate of change, super, super familiar to us, just the slope, okay? But what is this instantaneous rate of change, okay? So let's say, again, we have some function. And we'll call this f of x. And I was like, hey, here's a point, just 1 point. I'd like you to find the slope at that point. How did we find the slope at like just 1 point?
So far, we used like 2 other points that are close to that point and get the secant line of that, or the slope of the secant line of that, of those 2 points. So that's what we're doing.
Yeah, we said, here's 1 point, but like if we had another point that was like really close to it, we could use the secant line formula, right? Fall back on things that we know. Well, it turns out, so I'll go ahead and sketch this tangent line real quick. It should look something like this, okay? But the way we think about it mathematically is something like this. All right, so I'm going to go ahead and copy and paste this because I can. Thank you, technology. Oh, that's terrible. No. Okay, well, we're going to keep that green point then. I won't fuss about that too much, but I'm going to choose a point that is super, super close to the green point. Okay, So everybody see there's like a green point and a blue point here. Let's say that this green point I just called x comma f of x, okay? And I'm going to call that same point x comma f of x. Now, I'm going to be really clever about how I get to the blue point. To get to the blue point, I'm going to say x plus some value we're going to call h. Okay. If this x value is x and then the y value is f of x, what's the y value for an x value of x plus h?
F of x plus h.
F of x plus h. Take the x value, you put it into the function, that's what you get. Okay. This is kind of like when Dallas said 29 and 31, and someone else said 55 and 63. We're choosing x values that are close together. Okay. If I plug these 2 points into the secant line equation, I'm going to get f of x plus h minus f of x, right? That's the y value of one point and the y value of the other point, all over. What do I put in the bottom?
X plus h minus x.
So good. X plus h minus x. And this is our x value that goes with the green y value. And this is the x value that goes with the blue y value. Okay.
Can I ask something just because I'm curious? So the other point next to it, would it be x minus h and then the f of x minus h?
Oh yeah, we could do that way as well.
Okay.
We choose the one with the plus because even though we're all mathematicians, it's just easier to do things with plus signs rather than minus.
Oh yeah, I would rather do the positive side anyways.
That is exactly the mathematicians thinking. They were like, we could go the other way, but then we'd have some minus signs in there. So let's just go to the right and we'll make it positive. Okay.
Exactly.
All right. Now, wouldn't it be great if this green point and this blue point were like super close together? If they were super, super close together, they would almost be like the same point. Okay. So why did we start off with 2 weeks talking about limits? Here's why. If I want to find the instantaneous rate of change, that means I want to find the slope of, we don't call this the secant line, we actually call this the tangent line. Okay, so maybe let me write that up here. When I take the slope at just one point, I'm saying that's a tangent line. Okay, so when I take the slope of this, I'm going to do this, but I want this h to be as small as possible. And our fancy way of saying make this as small as possible a limit as h approaches 0 means I want that H value to get as small as possible. I want it to be as close to 0 as possible. Okay, so limits useful here because it's going to make the H values get as close to 0 as possible. How else could I write this denominator?
H.
Ooh, yeah, because look at this, x, whoops, x minus x we get just an H on the bottom. Okay. When someone says, find a slope just at one point, we do exactly what you all suggested. We find a second point super close to it. We use the slope formula that we know. And then we say, let's make these 2 points as close together as possible. And this will help us find that instantaneous rate of change. Okay. This is the story. This is the story behind what we're going to talk about next. Okay, so we're going to take a break. We've had a very full morning so far. We're going to take a break. We're going to come back and we're going to work on like the algebra side of this. Like we're going to look at questions that look like this and use what we know about limits to help us unpack that. But all we're doing is really finding a tool to help us find the slope at just a single point. All right. So gone are the days where we're going to need 2 points, but we're actually going to be able to squeeze those 2 points so close together they actually become one and work with this. Okay. So it is 10:49. Let's be back at 11:05. Okay, so let's be back at 11:05, and we will pick up with 3.2 when we come back. Okay, so I'll see you folks back here in about 15 minutes.